Hello, what I'm going to do in this video is go through simplifying radical expressions. So we're going to start with a perimeter and area problem using a geometric mean, and then we're going to walk through kind of an intro on how to simplify radical expressions by extracting perfect squares. And then we're going to use some of that and revisit the first problem and answer the question by expressing our answers in that radical form that we'll talk about, and then go through a couple more algebra problems. So with the first one, it's just an area and perimeter problem. So starting off with a couple of lengths here, what we want to do is figure out the perimeter of triangle PLW, so that is the big triangle here, and then we want to do the area of ALW, which is kind of the medium-sized one. So in order to do that, what I'm first going to need to do is figure out these three values, which I'm going to just call x, y, and z. So I'll start with the x value. Since I can focus on triangle PLA, I'm given a hypotenuse of 10, and I'm given one of my legs is 4 and the other length is x. So I can use the Pythagorean theorem to say x squared plus 4 squared equals 10 squared. That'll be x squared plus 16 equals 100. X squared is equal to 100 minus 16, which is 84. And then the directions do say that we're going to end up rounding the nearest hundredth. So if I take the square root of 84, that is about 9.17. So that gives me my first length. I'm going to keep that one kind of there, and keep in mind that this expression, really this AL going across here, is our altitude, since it goes from one of our vertices all the way to the perpendicular edge. So this altitude, and this is where the geometric mean comes in, this value is going to help us a bunch. So this altitude, if you take that 9.17 and square it, that is equal to the product of 4 and y. So what we already know though is when we take 9.17 and I square it, I get 84. So that kind of takes me back to this value right here. When we square rooted 84, we got 9.17. So I know if I can work backwards and square it, I'm going to get 84. And that is equal to 4 times y. So all that I have to do then is divide both sides by 4, and I get a y value of 21. So then what we can do is kind of look at the big picture here too, which is this giant triangle. And if we want to look at that, I've got 10 is my left hand side. I know that I have z across the bottom, and then this whole length then would be a little segment addition. I have the 21 and the 4, so if I add 21 and 4, I get 25. So I can do the Pythagorean theorem one more time and say 10 squared plus z squared is equal to 25 squared. And I'm going to end up with z squared is equal to 25 squared minus 10 squared. And that's going to be the square root, that'll give me 525. And then what we'll do is take the square root of that number, and I'm going to end up with z being equal to roughly 22.91. So that's going to give me that bottom value. And I can kind of replace that on my diagram then. So that's 22.91. So then from there we can answer the questions then. So kind of going back to this, where we wanted the perimeter of triangle PLW. So PLW is the large one. So that perimeter is going to be equal to 10 plus the 25, which was that entire length of PW, plus 22.91. And that's going to end up giving me a perimeter of 57.91 units. So that is for triangle PLW. And then the other one we want to figure out is the area of triangle ALW. So I'm going to just redraw that one down here across the bottom. So triangle ALW, if I labeled it, I would have A and then L, and then, L would be here, and then W would be here, because LW, that actually is backwards. Try one more time. So LW is my hypotenuse, and that's the 22.91, which we're not actually going to use for our area calculation. This would be AL going up here, and that would be a length of 10, and then this would be 21. So the area formula that we use is 1/2 the base, which is 21, times the perpendicular height, which is 10, and that's going to end up giving me an area of 105 units. So what we're going to do is just go through a little bit with simplifying radical expressions, and then we'll kind of come back and revisit this problem. So as far as simplifying radicals goes, what I'm going to do off to the side is write out all of my perfect squares. So I know that 2 squared gives me 4. I know that 3 squared gives me 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. And we could keep this list going on and on. I'm pretty sure as far as we go with, on this video, these are the only perfect squares that I'm going to be talking about. So we're going to take a look at this list. So what I have in blue is a list of all the perfect squares from the values of 2 to 7 and what their squares are. So I want to look, when I take a look at this expression radical 75, I want to know the largest of these values that evenly goes into 75. So we kind of go down this list and we say, okay, can I do 75 divided by 49 and have it come out as a nice even number? No, so then I go to the next one. Can I do 75 divided by 36? And that doesn't work. And then I get to 25, and I know that 75 divided by 25 is 3. So what I'm going to do is break this up into the square root of 25 times the square root of 3. Because I know that the square root of 25 times the square root of 3 is the square root of 75. So what I'm really doing is just breaking this up. And then we know that the square root of 25 is 5, and all we do is bring down the square root of 3. And that's it. That's the entire process of simplifying a radical. In this next example, we're going to do that same thing with the value of 28. So look at the largest perfect square that goes into 28, and that value is 4. So what I'm going to end up doing is taking radical 4 times radical 7. So since 4 times 7 is 28, and 4 is a perfect square, I can take the square root of 4, which is 2, and we just bring down the square root of 7. So on to these next couple. So with this next example, I have a 2 on the outside of this, and all that that's really going to do is turn into a multiplier, really. So I'm going to first go and figure out the largest square root, the largest perfect square that goes in 27, and that is going to be 9. And 9 goes into 27 3 times. So 9 times 3 is 27. I'm also going to bring that 2 down so that I don't forget about it. So the 2 just drops down. I know that the square root of 9 is 3. So what I'm doing is I'm dropping the little radical around that. Since the square root of 9 is 3, the radical goes away. And I bring down this 3 that was inside the radical. So then lastly, I just multiply the 2 times the 3 that are on the outside and get 6, and bring down my square root of 3. Then the last one, so this one's kind of got this little 6 over 4 here on the outside of it, which again, we're still going to start with the inside of the radical and kind of work our way. So I look at the largest perfect square that goes into 20, and you might be thinking like, oh, 10 times 2 is 20. The problem is that 10 and 2 are not perfect squares. If you take the square root of 10 or the square root of 2, you're going to get a pretty hideous number. So I think about the largest perfect square that goes into 20, and that is 4. And I know that 4 goes into 20 5 times. So I'm going to rewrite this as 6 times the square root of 4 times the square root of 5 all over 4. So I'm bringing the 6 and the 4 down, and I knew that 20 could break up into 4 times 5. So my next step of work is to take the square root of 4, which is 2, and bring down the rest of the problem. So nothing there. And then I'm going to multiply the 6 and the 2 on the outside, and that's going to give me 12. So I have 12 times the square root of 5 over 4, and then I can take this even one step further. The 12 is really a multiplier with the square root of 5, and the 4 is a division, it's a quotient of it. So what I'm going to end up doing is just dividing out 12 divided by 4, and that's going to give me 3, and then I can just bring over my radical 5. So that's really the whole process of simplifying radicals, which we're going to use then when we revisit the original problem, and we're going to determine this perimeter of triangle ALP. So from the very first problem, and kind of go back to this this idea that we're just going to use the Pythagorean theorem, and instead of taking a square root then, we're going to end up just simplifying the square root that we end up with. So going back to the original problem, we said x squared plus 4 squared was equal to 10 squared, and that turned into x squared plus 16 equal to 100. And then I took the 16 to the other side and got 84. So the difference here is when I take the square root of 84, I'm not actually going to go to the calculator. Instead, what I'm going to do is go down that list of all those perfect squares leading up to 84, and I think about the largest of these values Oh, I forgot 36. The largest of these values that evenly goes into 84. So I actually won't need the 36. 36 won't even evenly go into this. Neither does 49, 25, 16 doesn't go into it, 9 doesn't go into 84. 4 goes into 84, and that is 21 times. So I break this up then into the square root of 4 times the square root of 21. So the square root of 4 is 2. Bring down my 21, and that just makes up this one side length here. So I have 2 radical 21, and then keep in mind again, we just want the perimeter of triangle ALP. So the perimeter, I would take my 4 plus my 10 plus the 2 radical 21. And all that we can actually add here are these two integers 4 and 10. So then my perimeter is going to be 14 plus the 2 square root 21. So don't make the mistake of trying to go further and saying that this is like 16 radical 21. And the reason we can't do that is because the 14 does not have the square root of 21 attached to it. So this is your final answer. And that is, again, what we call simplest radical form. So we didn't take the square root and have to round and get decimals. We just looked for the largest perfect square that evenly went into 84. And with these last couple, it's going to be the same type of problem. So what we're going to do is use our geometric mean as well, but we're going to determine the values of x, y, and z and leave our answers in simplest radical form. So I'll start off with this first one. We're given that this entire base is 14 units. I'm given that this short part is 8. So what I can actually do is figure out this piece right here by simply taking 14 minus 8. So this bottom segment is going to be 6 units long. And then what I can focus on is figuring out what this altitude is. That was a horrible straight line. So going back, figuring out what this length of the altitude is, which is why we know that the geometric mean says I can take y squared and set it equal to the product of 6 and 8. So y squared is equal to 6 times 8. So y squared is equal to 48. And then since we want simplest radical form, when I take the square root of 48, we are not going to take the square root in the calculator and get a decimal. Instead, I'm going to go down that list again and figure out, and I can really keep this going if I wanted, and figure out what's the largest number that goes into 48. And actually, 4 does go into 48 12 times, but the problem is that 4 is not the largest perfect square that goes into 48. It's actually 16. 16 goes into 48 3 times. So when I rewrite this expression, I'm going to write it as the square root of 16 times the square root of 3. And I know that the square root of 16 is 4. So my y value ends up being 4 times the square root of 3. So I can go back to my diagram, and I'm going to just replace that value on the diagram. Is 4 square root 3, and then we'll get our next values. So we can get y and z now just using the, x and z using the Pythagorean theorem. Since x is a hypotenuse, and I know that because it's across from a 90, and same thing for z, it's a hypotenuse in the other triangle since it's across from my right angle, so we can use Pythagorean theorem for both of those values. So I'm going to figure out what x is next by writing out the Pythagorean theorem. That would say 6 squared plus this altitude, this 4 radical 3 squared, and that is equal to x squared. So working out these these squares, 6 squared is 36, and I'm going to be careful on this next one. If I were to square this value that's on the inside of parentheses, keep in mind that what you're really doing is multiplying it by itself. So this is the only time I'm going to really write this out, and then after this we'll kind of just apply the little rule. But by squaring a number, you are multiplying it by itself. And this is what I end up with. So it's really 36 plus, and then it's not like I have to distribute or anything, but just multiply your 4's, and that gets 16. And then multiply radical 3 and radical 3, and that gives me 3. And that is equal to x squared. And what we really end up with then is 16 times 3, which is 48. So that was the number before. If you keep in mind, that was the number that we ended up simplifying anyway. When we figured out that 16 was the largest square that went into 48. So it kind of takes you right back to that value. So if I were to hit this back arrow a bunch and kind of go back to that, just notice that we were at a step before, we knew that this value squared was 48. So later on, if you want to save yourself some work, which you could really do, is just replace this value then right here with the 48, and you don't even have to square it then. It would already be squared for you. So from here, what I'm going to end up doing is saying that x squared is equal to 36 plus 48, which is 84. And then I'm going to take the square root of 84 at the very end, and we've actually already simplified 84. We knew that 84 could get broken up into the square root of 4 times the square root of 21, and that ends up being 2 radical 21. So that is my x value. And I'm going to do that same process then to figure out what my z value is. So like I said, now I can apply that rule where if I focus on this triangle, I already know that I can take 8 squared, because that makes up this side, plus this y squared. Keep in mind, now I'm going to just kind of do what I did the flashback to. The y squared gave us 48. So I'm going to kind of say that again. The y squared comes from taking this value and squaring it, and we get right back to 48, and that is equal to z squared. So 8 squared is 64. When I add 48, I end up with 112. So z squared is equal to 112. So then z is equal to the square root of 112. And now you want to go down that list, and we want to figure out what is the largest perfect square that goes into 112. And if I take 112 and I divide it by 36, I get a decimal. If I take 112 and divide by 25, I get a decimal. 112 divided by 49 is a decimal. If I do 112 divided by 9, I end up with a decimal. So the one that's going to work then is actually if I take 112 and I divide it by by 16, I'm going to end up with 7. So the square root of 16 times 7. And we know that the square root of 16 is 4, and then I'm going to bring down my radical 7. So again, we're really just using the Pythagorean theorem a bunch over here and figuring out certain areas where we don't have to do so much work, like when I had to multiply this expression out. So we'll do one more of these examples. And in this part B, we're going to still solve for x, y, and z, leave our answers in radical form, except this time we're given some different information. So in this one, I'm given the 2 here, and this time I don't know this other piece, so I can't use geometric mean right away. But what I can do is focus on this small triangle that's to the right-hand side here, and I have a 2, a 4, and an x value. So if I realize that my 4 is my hypotenuse, since it's across from my right angle, I can write the Pythagorean theorem as x squared plus 2 squared equals 4 squared. That's going to be x squared plus 4 equals 16. X squared is going to be 16 minus 4, which is 12, and then x will be the square root of 12. So right away, I'm going to label that on my diagram, actually. We know that x is equal to the square root of 12. And that's going to help us later because, again, if we end up using that value and squaring it, we'll get right back to 12. So x is the square root of 12. And what I want to do is think about that list of numbers. So 4, 9, 16, 25, 36, 49. And I want to think about the largest of those values that is evenly going to go into 12. And that's going to be 4. And 4 goes into 12 3 times. The square root of 4 being 2. So my x value is 2 radical 3. So then now I can apply that concept of geometric mean. And that's going to help us figure out our y value. So I take a look at y is this part right here, and I look at the 2, and I look at the x. And that geometric mean said, hey, if I take x squared, that is equal to 2 times my y value. And we already knew that x was the square root of 12. So if I take the square root of 12 and I square it, just keep in mind that that's going to end up, the square and the square root will cancel out, and 12 is equal to 2y. So then my y value just ends up being 6. So I can throw that on my diagram, and then I'm going to just wipe this work right here from before. And then to get our z value, I'm going to just focus on, I'm going to wipe this, we're going to focus on this triangle here that has x, y, and z. And we knew that x was the square root of 12, we knew that y was 6, and z is my hypotenuse since it's across from the right angle. So I'm going to do 6 squared plus, and again, we know that I'm taking the square root of 12 squared, and that is equal to z squared. So I end up with 36 plus the 12 is equal to z squared. Z squared is equal to 36 plus 12, which is 48. And we've actually simplified that one before now. When I take the square root of 48, we go down this list and think about the largest perfect square that goes into it, and that is 16. So I'm going to break up 48 into 16 times 3, and then when I take the square root of 16, I get 4, and bring down the radical 3. So z is 4 radical 3. So just to quickly kind of recap everything in this video, we started with some perimeter and area problems, still using the same concepts of Pythagorean theorem and geometric mean, and the difference was with these problems we were rounding to the nearest hundredth, so then we went through just what it meant to simplify a radical expression and to break them up into perfect squares. And then we revisited some of the problems from before, or the first problem really, and just went through a perimeter problem, and then we wrapped up with a couple where we were using the geometric mean and Pythagorean theorem, and we were leaving our answers in simplest radical form.